Atomic spectroscopy. So when atoms or molecules absorb energy, that energy is often released as light energy. And we observe this in fireworks and neon lights. Each element emits a characteristic color. So here what we have to the right is three different lamps. They have gases in them. This has mercury, and this is helium, and this is hydrogen. And when you put a strong electric voltage across that, you can excite the atoms and they will emit energy as light. And we see that the different elements emit different colors. The different colors are different wavelengths of light, and they have different energies. This is a neon sign. Neon signs are that really bright orange because they contain neon, and that's the color that neon gives off. We tend to use the word neon to describe other things, but it's really just that color. So if we take the emitted light from one of those lamps and pass it through a prism, we get a particular pattern of wavelengths. It's called an emission spectrum, and that's going to be characteristic of that type of atom or molecule. It's not continuous like a rainbow. It's got bright lines at specific wavelengths, and in between there's just darkness. So it kind of looks like a barcode, and it can be used to identify a substance. These emission spectra cannot be explained by classical physics because classical physics just doesn't work here. So let's look at a diagram showing what's going on here. So here we have a lamp. This is a hydrogen lamp. We're exciting the hydrogen atoms with electricity, and they are emitting this kind of pinkish light. And we send that through a prism. The prism separates it according to wavelength, but instead of seeing a rainbow like we would with sunlight, we're just going to see a few specific lines. This red line would be over here in the red part if it was white light going through. And this sort of teal colored line would be over here, and then there's a violet line. The wavelengths are the same place on that screen, but the hydrogen only gives off a couple of lights, like 3 or 4, depending on how violet you can see. If we do that with helium, we see that we've got more lines. But again, there's big dark areas. Here's barium, we get a lot more lines. But this pattern is different than for helium. It's different than for hydrogen. So you can look at the pattern and identify what element it is. You can also get, here's oxygen and neon. And so neon's got some bands over here in the blue, but there's a lot of really bright ones over here in the orange. And that's why overall it gives us an orange color. You can also get an absorption spectra. So if you shine light on the element, you can measure the energy that's absorbed. And so for an absorption spectrum, instead of seeing bright lines, we see dark lines where the energy was absorbed by the element. But they'll line up in the same place as the wavelengths are the same. So flame tests are not as fancy. We don't see discrete lines, but our eyes perceive, I keep hitting the wrong button, our eyes perceive the colors as different. So sodium always gives off this orange-yellow color. It's very distinctive. Potassium is a lovely violet color. It's really hard to get a good look at that. Lithium is this beautiful red. Barium kind of has a greenish color to it. So you can use a flame test to say, oh, well, that's obviously not lithium, right? Barium is that color. There's several that are red, but they're slightly different reds. So of course we can take that fun color stuff and make it into math, right? And ruin everything. So Johannes Rydberg analyzed atomic spectra, and he's like, okay, how can we describe these wavelengths mathematically? There's got to be some pattern.